Okay, so we've already deleted 2 versions of this video because of accidentally swearing at it, so we're off to a good start. For the last part of today's lectures, I want to talk about cross products. The concept of a cross product is very useful in 3D. It gives us a particular way to combine 2 new vectors and make a third one. And so, given vectors v and w, we have a cross product vector that has 3 major properties. It's perpendicular to both of them, so it's a new vector that makes an angle of 90 degrees with both of them. Its length is equal to the length of the first times the length of the second times the sine of the angle between them, where we either use absolute value of sine or we measure angle between 0 and 180 degrees. And it also has the property that those 3 vectors have to form a right-handed triple. So for vectors v, w, and v cross w, if I try and make a right-handed triple, I put my thumb in the direction of v, and then my index finger in the direction of w, and then my middle finger should automatically pop up and point in the direction of their cross product of v cross w, which is not ideal to demonstrate in front of a screen, but that is what it is. There's a formula for cross products, and the reason that cross products are so useful is largely because their formula is actually relatively straightforward. So just like the textbook does, I'm going to think of I, j, and k, these 3 standard vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. I'm going to think of these as having names I, j, k, and I can express a general vector as some combination of adding up I, j, and k. And the textbook loves this notation. I'm less enthusiastic, but it's kind of stuck around for a couple of hundred years due to over-enthusiasm about the quaternions. If we have 2 vectors, a, b, c, and d, e, f, we can put them as row vectors in the bottom of a 3 by 3 matrix, and in the top row we put these 3 standard vectors, I, j, k, and then we take the determinant. We step through the first row, we multiply I times the 2 by 2 matrix we get by leaving row 1 and column 1 out, and then minus j times the vector we get by leaving row 1 and column 2 out, and then k times the third 2 by 2 determinant. It expands out to a formula that looks like this, but nearly nobody actually remembers the formula that way. They remember the determinant formula because it's much cleaner to think about. And cross products are handy not just because they construct a third vector that's perpendicular to the other 2, but they have a handy formula in terms of area. Meaning, if we take 2 vectors v and w, v times w times the sine of the angle between them, in terms of trig, is the base times the height of the parallelogram they make. And so if I want to know the area of a parallelogram, I find the 2 vectors that give me its sides, I take their cross product, v cross w, and then I take the length of that. That gives me the area. Whereas on the other hand, if I want to know the area of a triangle, I find vectors that give me 2 of its sides, and then I can take the cross product and divide it by 2, because the triangle has half the area of the parallelogram. And so that makes it very handy for finding information about these shapes in 3D. Now, the length of a cross product never gives me a positive or negative number. It always gives me a positive number, and that reflects the fact that unlike in 2D, there's no way to tell about orientation. If I have 2 vectors v and w that are pointing in random directions, there's no way to decide clockwise or counterclockwise because they could be pointing just randomly somewhere into 3-dimensional space. All right, thank you. That's it for today.